Okay, so what we're going to do now is we're going to examine the operation of BGP. So this little bit we're just going to talk about now is not really MPLS. What we're doing is we're going to look at BGP, and the reason we're looking at BGP is because it is BGP that is going to direct traffic into our label switch path. So once we get our label switch path set up, we need a mechanism of getting the traffic into the label switch path. That's going to be BGP's job. So let's just get in. I'm going to take a look at BGP. We're going to look at an issue that we always have with BGP and how to go about resolving this particular issue. So here's our network here. We've got site 1. We have got our provider, and then we've got site 2. And you will notice that each of these are a different autonomous system. So of course it's BGP's job to get the traffic between those autonomous systems. So here we have site 2 is advertising via BGP, advertising so the reachability to site 2 is being achieved via BGP. So the router in site 2 advertises to R5, which is in our provider core. So what happens is R5 then receives this BGP route advertisement via its eBGP peer with site 2. R5 then re-advertises that particular route to R1 via its iBGP peer with R1. So that's internal to the provider, to this particular service provider. So then, if we take a look at R1, what we find is that R1 has a route to site 2, which is the 64.25.1/24 network. It has a route which it has received via BGP, but that route is marked as unusable. Okay, so in other words, what it's saying is, yes, I've received a route from R5, and I have received this particular route, and it tells me of a path to 64.25.1, but I can't use that. So let's find out why R1 can't use that particular route. So if we go and take a look at the show route extensive for that prefix, we find that the next hop type is unusable, and what we discover is that the next hop is in fact 182.19.200.2. So why is that the advertised next hop? Let's go back and take a look at that slide. Let's take a look at the network between R5 and site 2. What we'll find is that network is 182.19.200.0 network. Okay, so we can assume that on this particular point-to-point link, that R5's address is .1 and that site 2's address is .2 on that network. And as you may recall, with eBGP peers, the peers are set up between the physical interfaces across the eBGP link. So one side of that peer is going to be 182.19.200.1, that's the R5 side. The other side of the peer will be 182.19.200.2, which is on site 2 side. So what happens is when this BGP advertisement arrives at R5, the advertisement says that the network 64.25.1/24 is reachable via the next hop of 182.19.200.2. So R5 receives this advertisement. Now R5 is perfectly fine with that because R5 has got a point-to-point link to that particular network. So R5 has got a direct route to that network by virtue of the fact that its interface that connects to site 2 is participating in that network. So R5 has got a direct route to that next hop address. The issue is though, once that route is re-advertised over to R1, R1 does not have any way of reaching or any information as to how to reach 182.19.200.2. Why doesn't R1 know about that? Well, because the information that R1 knows about is the information that it has learnt from its own IGP running in its own network. And it hasn't learnt about that network because that network, the 182.19.200.0 network, is not part of the IGP that is running within that autonomous system. Now you might say, well, why isn't it part of that IGP? It could be. Well, could it be? Well, yes, it could be. But what's happened is that particular link from R5 to Site 2 has not been included in the IGP for that provider's autonomous system. Now, it could be. Yes, it could be. So one way of solving the problem would simply be to include that network in the IGP and have it as a passive interface. And that would solve the problem. That's one way of solving the problem. But the problem we have, just looking at this, the problem we have is actually a BGP problem. So, you know, and what we would kind of rather do is solve the BGP problem with a BGP solution rather than solving a BGP problem with an IGP solution. So let's just take a look at that particular issue there. So here we are looking at the show route extensive. We find that we have an indirect next hop here of 192.168.1.5, and we've got a next, and we have information as to how to get to that particular next hop. Let's get back up to here. So what we're saying here, the solution is to add an export policy on R5 to change the next hop to self. Now, as you may recall, that when BGP advertises an IBGP route, it does not modify the next hop information. That is the default behavior of BGP. When BGP advertises an eBGP route, so when Site 2 advertises to R5, the next hop is updated to the external address that is attached directly to R5. But when R5 re-advertises the route to R1, the default behavior of BGP is to not update the next hop information. So by simply changing that default behavior on R5 and putting in a policy which changes the next hop to the address of R5, we can solve that problem, and the result is that we now have the next hop for that route being the loopback address of R5. And R1 has reachability to that address. How? Because it has that reachability via its own IGP. And that's why it is always best practice to include the loopback interfaces within your IGP. So if your IGP was OSPF, you would simply include your loopback interfaces in the OSPF protocol, so that those networks, those addresses will be advertised via your IGP. Now, it is usual practice when establishing IBGP peers within the autonomous system to establish the peers between the loopback addresses of your IBGP routers. So the peering is between the loopback address, in this example, the loopback address of R1 and the loopback address of R5, which is why R1 now has reachability to R5 wireless loopback address. Okay, so then now that we've solved that little BGP problem, we can now get on with configuring up our static LSP. Okay, so what we have here is an LSP, our static LSP. Let's take a look at R1. R1 is our ingress router here. So we have got static LSP with a very creative name of My LSP. That's the name of our LSP. Ingress, so we're configuring this on R1, which is our ingress router. The next hop is 172.20.0.2. As you can see, the link between R1 and R2 is the 172.20.0 network, with R1 being .1 and R2 being .2. So that becomes our next hop of our path. Then we have the to statement, and then we have the IP address of the egress router. Now we're going to reference the loopback address of that router, which is R5. Over here, 192.168.1.5. It would be kind of useful, I realise, if the addresses were included on the diagram in the slide. Okay, but we're just kind of just look at that loopbacks 192.168.1.x here. So R5 is 192.168.1.5, which is the loopback address of R5. And then we have the value of the label, which is a push statement, and the value of 1000050. So that sort of sets up the label switch path, because we're setting that up on the ingress router. And then if we go and take a look at our transit router, there on R2 we have got the label switch path name reference there. We have the transit statement, then we've got the label value that we're expecting to receive for this label switch path. Next hop router, so next router along, and then we've got a swap value. Okay, now we arrive to R4, and you notice that the transit statement is there. The value that we see there is the value that was swapped by R2 and put onto the label value that R2 put onto the packet, which is now being received by R4. So R4 will do a lookup based on that label information. The next hop, 172.40.0.2, and the pop statement. So there is no swap, just a pop statement. So with R4 being the penultimate router, it's popping the label, so you don't have to you don't configure an LSP on the egress router. So essentially, the egress router will just forward that traffic as usual. Okay, if you do a go to R1 and do a show route to 192.168.1.5, what we've got is in our INET 0 table, we've got our IGP, which in this case is OSPF. We've got our IGP giving us a route to that address, and the next hop is 172.20.0.2. So we have reachability to the 192.168.1.5 address via our IGP. Now, why are we looking at that address? The reason we're looking at that address is because that is the egress route on our LSP. So that is the destination, if you like, of the traffic that's going on our label switch path. So we have reachability via the IGP. However, we also have reachability via the INET.3 table as well. So the INET.3 table, we have this MPLS route, which is to 172.20.0.2 via GE1060. And we have this push statement on that there. Okay, so even in the routing table, the push statement is recorded. So if you take a look at the metrics of OSPF, we have a metric of 3, and we have a route preference of 10. And if you take a look at the MPLS, we have a metric of 0 and route preference of 6/1, what we find is that the MPLS route has got a better metric. Okay, and because it has got a better metric, then it is the route that is selected. So even though we have the ability to reach our destination via our IGP and also via MPLS, it is the MPLS that's got the better metric. And as you know, the lowest preference wins. So BGP installs the LSP as the next hop. So if we do a show route 64.25.1.0/24, we will find we have a BGP route. Now we're running this on R1. We have a BGP route, and the next hop is to 172.20.0.2 with the push statement on there, which signifies that this traffic is going into that label switch path. So the label switch path then is the next hop for the traffic. So traffic that is destined for 64.25.1.0 is going to be forwarded or going to be directed by BGP into this label switch path. So here's the deal. The traffic has arrived from site 1. It has arrived on R1. The destination address on the packet is for the 64.25.1.0 network, which resides over here in site 2. Okay, so it arrives with that address. R1 looks at that IP address, looks at its routing table, finds the route finds a BGP route which will direct traffic into that label switch path. Okay, so its next hop is to go into the label switch path and then traverse that network. So after it enters the label switch path, it will no longer be forwarded based on its IP address. It will be forwarded based on its label. So that then gives us total control of where and how we direct that traffic through that internal provider's core network. Okay, so it is the job of BGP to direct the traffic into the label switch path. Okay, so the traffic. So what we've got is two things going on here. We've got the route advertisement coming out from site 2, BGP. So we've got the eBGP advertisement arriving at R5, the iBGP advertisement arriving at R1. We've done a next hop self on R5, so we've put a routing policy on R5 to change the default behavior of BGP, which is to not change the next hop. We've changed the default behavior to change the next hop to itself. It then advertises that route to R1. R1 has reachability to R5 via the IGP that is running within the provider's core network. So we are relying on the IGP, still relying on the IGP to give us a connectivity around our network inside our autonomous system. So R1 now has a usable route over to site 2 via R1 as its reachable next hop. So traffic then arrives from site 1, hits R1. R1 says, yep, I have got a route to that particular destination in site 2, and my next hop is the label switch path. So it puts the traffic into the label switch path. It then uses labels to forward the traffic all the way through, pops it at R4, arrives at R5. R5 then uses its BGP routing table to do a lookup and directs the traffic over into site 2. Okay, so we've got routing advertisements going from site 2 over into our core. So routing advertisements going one way, and there's traffic then going up the other way. Okay. Alrighty. So let's have a bit of a recap of what we have learned so far. The ingress router behavior. We'll get into these things called signaling protocols in our next lesson, but here's an example of them here: RSVP and LDP signaling protocols. They signal the LSPs to. What they do is they basically automatically set up the LSPs. So instead of having to go into each and every router along the path and configure, this is my transit label, this is my next hop, this is my swap value.
You have to do that?
Well, that's static. That's the static one, okay? So we're going to do that for our first lab, just to get the hang of what's happening. But what these signaling protocols do is they actually configure all that for you. They'll actually go up and configure your routers for you and put all the information in there. So very nice. So you see that working. So that will actually signal up the level switch path for you. And we're going to install the IP prefix to the egress router into the INET.3 routing table. So this is all happening on the ingress router. Specifies the LSP's egress interface and label assigned by the downstream router. So we've got a couple of routing tables going on here. We've got our routing table which is used by our IGP and BGP, which is INET.0, and we've got a routing table used by MPLS, which is INET.3. Okay, so then what happens is BGP performs a recursive lookup to resolve the BGP next hop. What's a recursive lookup, by the way? What do we mean by that? A recursive lookup. Let's go back and look at our diagram. Okay, so what's happening here is R1 says, okay, I have got a next hop to this network over here in site 2, and my next hop is this address over here on R5, okay, which is 192.168.1.5. Now, R1 does not have a BGP route, or put it this way, the BGP route says your next hop is R5, but guess what? R1 is not attached to R5, is it? It's not directly connected to R5. So it can't send traffic out an interface directly to R5. So what it has to do is say, okay, now that's great, but how do I get to R5? It now has to look in its IGP routing table to figure out how to get to R5. That's called a recursive lookup. Okay, it says, yes, there's my route, it's to R5, but now my problem is, how do I get to R5? Oh, let's go and look up that. That's a recursive lookup. So here, so BGP favors routes in the, let's go back to here. So BGP favors routes in the INET.3 table. MPLS preference is better than ISAS and OSPF. For preference ties, BGP always selects the route in the INET.3 table. And the LSP to the egress router is copied into INET.0 as a forwarding next hop. And specified LSP's egress interface and the label to push. So all that goes into the routing table and the forwarding tables. Okay, so the INET.3 information is updated into INET.1, which updates the forwarding table. Okay, there it is there. So in our forwarding table, we see the destination prefix and the my LSP label switch path with the push label value. Okay, so route resolution summary. Look at this. LSPs are installed in the ingress router's INET.3 table. Point to the IP address specified as the egress router on the LSP. Normally identifies the egress router's loopback interface, as we've seen, using the loopback interface as the egress router's address in our LSP. Address appears that we're directly connected. So when the LSP is up, the next hop is usable and attracted to BGP. When the LSP is down, the LSP's next hop is unusable. You can still use normal routing to reach the next hop. So only BGP then is aware of labeled switch paths. The other protocols can use the information with additional configuration. So by default, it's only BGP that is aware of the existence of labeled switch paths. And why is that? Well, only BGP has to be aware of that because labeled switch paths are used for transit traffic. So traffic coming from one autonomous system into another autonomous system, okay, which is always handled by BGP. So it's only BGP that really has to be aware of LSPs in order to direct the traffic into the LSP. Okay, so the routing table summary, we've got INET.0, which is the usual primary unicast routing table. We can install additional prefixes per LSP if we need to. INET.3 is the MPLS routing table. Houses signaled LSPs at the ingress node and can install additional prefixes per LSP. So it handles these signaled LSPs. We haven't really got into those yet, but we will. MPLS.0 is the MPLS label switching table used by transit and egress routers. So that's where the label value is associated with the egress interface on the router. So that's the next hop lookup based on label value. Okay, let's go and work through, just go through the process and look at how MPLS packet forwarding works. So here we start with our ingress router. The ingress router performs a forward lookup based on the destination IP address. So the packet arrives at the ingress router and it's going to do a lookup based on the address. It will result in the INET.3 or INET.0 routing table. After the next hop is determined to be the LSP, the MPLS header is then added and the packet is forwarded with the corresponding label. So that will be determined by the information in the routing table. It will determine that the next hop is an LSP. Okay, so if we go show route table INET.3, we will find that we have this MPLS route in here, and the next hop is an LSP because we can see the push state on that next hop. Okay, on the transit router, it performs lookup based on the incoming label, and that results in the MPLS routing table. So that's the only lookup that it needs to do. Label handling depends on the LSR type, so the transit will swap out the incoming label with the outgoing label and forward the packet to the next router. If the transit router is also an ultimate router, it will usually pop the label and forward it to the egress router without a label. And the egress router will simply do a forward lookup based on the destination IP address, which it will resolve in INET.0 or INET.3. Okay, so the MPLS label mapping is handled by the MPLS.0 table that contains the mapping information of incoming labels to outgoing labels and next hop information is used to forward the MPLS packet. So also known as the LIB or the label information base. But its real name, its actual name is MPLS.0. So we do a show route table MPLS.0, find our MPLS values in there. This is on R2, which is a transit router. So we're going to see that we've got an incoming value, we have got a next hop, and we've got an interface, and we've got the swap value. Now, penultimate hop popping. So penultimate hop popping is the default behavior in the Junos operating system, and let's just go does exactly the same thing. Penultimate router pops the MPLS label and forwards it the native IP packet to the egress router, which then makes its forward decision based on the IP header. That's R5. And we've got a pop statement there at R5. Okay, let's take a look at this idea of implicit and explicit null labels. So with an implicit null, the default operation in the Junos operating system, the egress router signals the penultimate to perform the label pop. So that's the implicit null value, which is a 0, and the explicit null configured on the egress router signals penultimate router before the packet with an MPLS tag. So the usual behavior is the implicit null. But there are times when we may actually want the packet to go to the egress router with the MPLS header on, and that will the egress router will then pop the label. Okay, so this is already just a bit of an introduction to the concept of MPLS. So we looked at the common terms. So we looked at labels, LSRs, label switch routers, label switch paths, the label information base, the LIV, concept of an ingress router, the egress router, the push at the ingress, pop at usually at the penultimate, a swap by the transit routers. We looked at the concept of the fact that it's usually the penultimate router that pops the label, and the fact that the implicit null is the value that it tells the penultimate router to pop the label, and it's the explicit null which will actually signal that the egress router should pop the label. We had a look at the way that the label switch router forwards MPLS packets, looked at MPLS packet flow, so packet processing from ingress right through to egress. Look at some of the configuration on how to set up a static label switch paths, which we will do as one of your very first labs actually. We'll get into setting that up. And we looked at the label information base. In fact, one of your very first labs is to go and configure the interfaces on your router. You will set up your IGP, which will be OSPF, so you'll get that up and running. Then what you'll want to do is you want to set up BGP peers between your autonomous system and the port provider that you're actually going to be working with. So you'll set up your BGP peers through there. And once you've got all that working, you'll do some connectivity checks, you'll do some BGP route advertisements to make sure that route advertisements checks to make sure you're getting advertisements and receiving advertisements from your partner's device. So you should be sending and receiving both ways. You'll check all of that, and then once all that's running, you're now ready to build your static label switch path. Okay, and then what will happen is BGP will then direct the traffic into that path for you, and then you can check that the traffic is in fact going through that path. So you'll be able to do some traffic checks to make sure that in fact that is your next hop and that it will be directed into that path. Okay, so some review questions here. How does the ingress label switch router make forwarding decisions? Okay, so we did talk about that, and there was a particular routing table that we referenced, which was the, you might remember, the INET.3 routing table, and that is what BGP uses to look up, or as its preferred routing table, to look up routes, and we will discover that the next hop is a ladder switch path. What is the default behavior for the Junos OS for popping labels? Okay, so which router pops the labels by default? What do we call that router that pops labels? It's called the penultimate router. That's the one that pops the labels. Okay, second last one. Second last router pops the labels, which is called the penultimate router, so the penultimate popping. What routing table does a transit router use to make forwarding decisions? Okay, this is an easy one. What is the name of the routing table that a transit router uses to make forwarding decisions? MPLS.0. Yes, that's what it's called. MPLS.0. Okay, so we're going to do some labs on that. Now, just while we're talking about labs, let's just dive in and have a look at what that might look like. I'm just going to open up PuTTY, and I'm not actually going to do a lab, but I'm just going to kind of show you how you would get started to do a lab. Let me first of all go to my addressing table for our labs, and I need to put everybody into a pod here. Oops, where am I going? And my addressing table will be down here. There we go, class pods. Let's open that up. Alright, so I've assigned the first group here. We've got Tom and Lydia. In that group, I need to put a couple more people into groups here. So what I would like to do is to get at least the first 24 students sorted out as quickly as possible. So if you have a preference as to who you would like to work with, please discuss that amongst yourselves and email it to me. Okay, and then I'll put you into your appropriate groups. Okay, so there's 2 people per group. That's how it's going to work. So each of you are assigned to a particular device. Alright, so you'll be configuring a device. So in this case, let's look at our first group here. We've got Tom. He's going to be configuring device. Well, he's on the MX1 device in his pod, and Lydia is going to be on the MX2 device in that pod.
Me and Renat as well.
Okay, you want to go here?
Yeah.
Okay. So you got Daniel and Renata. Alright. So we'll put you there. Okay, so let's just take a bit of a look at this pod here. We're going to open up PuTTY to that address, and let's open it up. I am going to log in to PuTTY. Let's bring PuTTY over here. There we go. So the login is lab. Oops, should be. And the password is lab123. So exactly the same as what we've been using all along. There we are. I logged in. I've actually got started with the first little bit of the very first lab by just configuring up the interfaces. So I'll just do a show interface terse. right there, and we'll see that I've actually gone and put the addresses on this first interface GE000. So I've created unit 210 and I've configured an interface, put the address on that interface. I've done the same for GE001.211. So I've created unit 211 and put the IP address on that. The other thing is we just go into the configuration mode and show you something that we're doing here with the interfaces. Just do a show. We're actually setting up a VLAN tagging on these interfaces as well. So unit 210, VLAN tag 210, and they're putting the address on the 172.22.210.1. And that relates back to our diagram, which I will have to just go and get our diagram up here. Let's go and find that again. Let's go there. Let's go down to, actually to go up here. I need to go to my lab diagram. So I want, let's get that around the right way. Okay, so this is I'm actually excuse me, logged into MX1. I've configured GE. Now on the diagram, you've got 100. The real name of it is 000. This diagram is, as I said, published by Juniper, and they just do things a little differently because they use actual physical equipment which has different interface numbering scheme. Ours, all our interfaces begin with 0, not 1. So I've actually got 000 here. I've got my IP address configured there, and that's attached or directly connected to this other device here. So this is one device. This is a completely different device here with this P1, P2, P3. That's already pre-configured. So that is the provider core that is already pre-configured. You don't have to ever do anything with any of this in here. That is fixed. Okay, that's already pre-configured. It's all there, all working. All you're going to configure is your device, the MX1 and the MX2. That's all you're going to work with. So I've put the IP address on GE000, and what I should be able to do is I should have connectivity here to 172.22.210.2. So I should be able to ping that address, and there I am. It's up and running. So what I'm pinging there is very simply pinging across this link right here between MX1 and this P1 device over here, which is actually a it's kind of like a virtual machine that runs inside of the router. So each router kind of like has, with these MX routers, you can configure multiple virtual machines to run in them. So this device is what we know, what we are calling the VR device, which is simulating a telecommunications network, or telecommunications core network. So there it is. It's pinging away merrily there. Let's stop that. Okay, so I should also be able to ping the other interface, which is the 11. And there we are, that's also working. So that's this other link down here on GE001, and I'm connecting into this P4 device down here. Okay, so that's one of the first checks you're going to do. You're going to make sure that you've configured your interfaces correctly and you've got connectivity into the core network that you're supposed to be connecting with. the next thing you're going to do is you're going to go ahead and configure OSPF. And once you've configured OSPF, you should then have connectivity between your two MX devices at that point. So because OSPF is already configured in the core, by configuring OSPF on MX1, you then set up a neighbor relationship with this core, this provider core, and MX2 will set up a neighbor relationship, and therefore the OSPF routes will be advertised right across that whole system there. So you will achieve connectivity between the loopback interface of MX1 and the loopback interface of MX2. So in other words, you should be able to ping each other's loopback interfaces. Okay, and that's just a really good test to make sure that you've got OSPF up and running and all the other connectivity is up and running. So you want to do that, and then you'll go ahead and you'll then set up BGP peers between this autonomous system over here. Actually, is that what you're going to do? No, probably not. I think the next thing you're going to do is actually just set up a label switch path. Yeah, that's the next step. Right after that. So here we go. Okay, that's so that's going to take care of part one, our static LSP. Once we get into part two, then we'll start creating this other entity over here, this CEX entity. By the way, this terminology here, PE is an abbreviation for provider edge. So what we're really doing here is this router, this MX1 router, is acting as a provider edge router. And then within it, we're creating a virtual router instance down here, which we're calling CE. So we actually called CE1-1, and that provider entrance, the CE, is an abbreviation for customer edge. So that's going to simulate a customer's network or a customer network, and we'll go ahead and give that a completely different autonomous system, which then allows us to set up a BGP peering arrangement between the CE and the PE, which is basically that's exactly how it would work in practice. And that's going to allow us then to direct traffic into our static LSP that we've just created. Okay, so we're going to create our static LSP up here, and then we're going to go ahead and use BGP, this BGP peering arrangement that we're going to set up. We'll use that to direct traffic into our label switch path. So you actually see how BGP handles that and directs traffic into the label switch path. And then we will get into label distribution protocols, otherwise known as signaling protocols. That will be, in fact, that's our next lesson. So we'll get into signaling protocols next and have a look at how they work. Okay, but it's important to get into these labs. There's quite a lot of labs to do here. One of the things I really wanted to point out as well, before we start anything, is that one of your or your major assessment, your major accessible item or accessible, I guess the evidence that you need to provide for the assessment is in fact your labs. Okay, so as you go through and do your labs and get to a point where you say, okay, now I've created my static LSP, it's up and running, what I want you to do is I want you to take a screenshot of your verification that your static LSP is up and running. Okay, so there will be verification steps in the lab. So I want you to take a screenshot of that and say, yep, here is my static LSP up and running. Okay, and as we go through and set up our BGP peers, okay, here's my BGP peer set up and running. Okay, so I just want to see those steps as you go through. So you're going to be taking quite a lot of screenshots as you go through here. I would recommend that you use something like snipping tool for that, rather than just taking the whole screenshot. kind of works a lot better. Okay, so we're going to take a break, and when we come back, we're going to take a look at these label distribution protocols, otherwise known as signaling protocols. So we'll get into that when we come back.